The James Webb Space Telescope has made a sensational discovery by capturing a large object located approximately 10 light-years from Earth, which is moving in our direction. Reports indicate that the telescope has detected changes in the trajectory of this object. This new finding has once again astonished astronomers and deepened human understanding of the cosmos. When astronomers first took notice of the interstellar object named 3I Atlas, its existence already contradicted conventional beliefs. The observational results were astounding. The object was discovered on the 1st of July as part of the Atlas survey funded by NASA. It turns out that 3I Atlas is much larger than initially thought. This discovery has sparked genuine excitement in the astronomical community, not only due to the fact of the discovery itself, but also because it points to a hidden diversity of bodies wandering through interstellar space. 3I Atlas was already of interest before being studied by the Webb Telescope, as it is only the third confirmed interstellar object in our solar system, carrying with it the mystery of the cosmos. Unlike asteroids and comets that orbit our sun and fit into known models of planet formation, interstellar objects originate from entirely different stellar systems. They are ejected into the galaxy during the early stages of star and planet formation, and then drift in the darkness between stars for millions, and sometimes even billions, of years. Therefore, each such object passing through our solar system becomes a rare messenger carrying physical evidence of conditions that existed far beyond the influence of our sun. Studying 3I Atlas presents a unique opportunity, but observations using the Webb Telescope revealed sizes and structures that no one expected to see. Astronomers have already attempted to determine the size of the object. Initial measurements based on data from ground-based telescopes and preliminary light curves suggested that it was no larger than a typical comet nucleus. This aligned with expectations, as the first two discovered interstellar objects, Oumuamua and 2 Iberis, also had sizes characteristic of small bodies in the solar system. However, the infrared instruments of the Webb Telescope provided a new level of sensitivity, allowing for the differentiation of faint thermal signals against the backdrop of cosmic darkness. It turned out that 3I Atlas reflects and emits much more than one would expect from a small body. Calculations showed that its size significantly exceeds initial assumptions, and it possesses a complex structure. This discovery is of immense significance. A larger interstellar body challenges traditional notions of what materials can be ejected from forming stellar systems. Most models suggest that during gravitational disturbances caused by planet migration, small icy or cometary fragments are ejected. However, 3 Atlas, with its unexpectedly large dimensions, suggests that entire planets or planetesimals may be ejected into the interstellar medium. If this is indeed the case, it indicates that the galaxy is populated not only by dust particles and small debris, but also by colossal wanderers that silently glide between the stars. The mere existence of such a large object compels astronomers to reconsider the mechanisms of planet formation and the dynamics of young solar systems. Another astonishing discovery made using Webb technologies pertains to the surface and composition of this object. By analyzing the spectral characteristics of light reflecting off 3 Atlas, scientists found a mixture of features characteristic of both icy volatiles and darker carbon-containing compounds. This is unusual, as such a combination suggests active thermal and chemical processes. The fact that these compounds have been preserved on an object of this size supports the hypothesis that it may have originated in a parent system rich in both ice and complex organic materials. The presence of organic material on an interstellar body of this size heightens interest in panspermia theories, which propose that the seeds of life may spread across galaxies via wandering bodies. If objects like 3 Atlas are not rare, then the likelihood of interstellar exchange of organic material and even biological molecules becomes more probable. The size of 3 Atlas also impacts detection issues. Small interstellar bodies are difficult to notice until they enter the solar system, and even then, they often quickly disappear from view. In contrast, larger objects retain their brightness longer, provide a greater surface area for sublimation of gases, and leave more noticeable traces of activity. This helps astronomers track their movement more accurately and allows for more observation time. The detection and confirmation of the scale of 3 Atlas using Webb technologies serve as a reminder that the interstellar medium contains many more bodies of significant size. Objects that we will be able to detect with greater reliability as telescopes improve raise broader questions within the scientific community about the statistics of their population. If 3 Atlas is significantly larger than expected, is it a rare exception, or does it indicate the existence of an entire category of massive interstellar wanderers? Previous discoveries have focused on smaller objects, as they are more common and harder to detect. However, the discovery of Webb technologies prompts astronomers to consider that large interstellar planetesimals may be more abundant in space than existing models have predicted. Thus, the galaxy may turn out to be far more populated than previously thought. It is filled with silent giants, moving along gravitational trajectories shaped by collisions with distant stars. For planetary defense researchers, this discovery holds another important significance. An object of such size entering our solar system raises a crucial question about the possibility of a collision, as the likelihood of this remains extremely low. However, it prompts us to consider the predictability of the appearance of foreign objects in our near space. Observing large interstellar bodies becomes important not only due to scientific interest, but also for understanding their trajectories and potential impacts on comets and asteroids within the solar system. The interaction of such a massive object with the gravity of our Sun can significantly alter the orbits of local bodies, adding a subtle yet important complexity to long-term celestial mechanics. The James Webb Space Telescope has proven particularly effective in revealing a variety of phenomena in our universe. With its outstanding sensitivity, it not only refines previously obtained data, but also completely changes our perception of information. In the case of the 3 Atoloses, Webb confirmed their sizes and demonstrated that our earlier assumptions were not entirely accurate. Now, each interstellar object is perceived not as something strange, but as part of a vast cosmic narrative. The sizes of the 3 Atoloses alter our understanding of the galaxy, showing that the process of planet formation occurs not only violently, but also with the ejection of large fragments into the void. The study of these objects also emphasizes the importance of timing, as interstellar bodies quickly pass through the solar system, following hyperbolic trajectories that provide only limited opportunities for observation. The fact that Webb was able to gather precise data while the object was within reach underscores not only the readiness of the scientific community, but also the importance of coordination between ground-based and space observatories. Each new interstellar object becomes a test of our ability to respond promptly, rapidly collect data, and adapt models based on unexpected discoveries. As the 3 Atoloses turned out to be significantly larger than anticipated, this creates a foundation for future encounters, where the unexpected becomes the norm. Looking to the future, it can be said that this will influence broader interest in the study of exoplanetary systems. Each observed large interstellar object represents a tangible part of the history of another system, a sample of material formed by processes occurring light years away. If the 3 Atoloses formed in a protoplanetary disk similar to ours, then the preserved materials may indicate common processes, or conversely, their uniqueness. By comparing its spectrum with known spectra of comets, asteroids, and other objects, scientists can identify similarities and differences that define the process of planet formation in the galaxy. The discovery of such magnitude ensures that comparisons will not be superficial. The larger the body, the more representative it becomes for the building blocks that form entire systems. The cultural and philosophical resonance of such a discovery cannot be overstated. Since ancient times, humanity has gazed at the stars with reverence and curiosity. However, the revelation that entire worlds, composed of material particles, wander among the stars, makes the galaxy both more immense and interconnected. The thought that 3 interstellar objects could have originated in a distant system, orbiting their star, and then embarked on a journey lasting millions of years before reaching the solar system of Earth is truly awe-inspiring. Their colossal sizes only enhance this perception, indicating that what we observe is not merely a pebble from another world, but a significant fragment of cosmic history. The confirmation of the true scale of the three interstellar objects by the James Webb Space Telescope marked one of those pivotal moments when scientific discoveries reshaped the boundaries of our understanding. Instead of comfortably fitting in to known categories, this interstellar object expands the horizons of research. It hints that there may be far more massive travelers in the galaxy than previously thought, and that planetary systems are capable of ejecting enormous bodies into interstellar space. This suggests that the mechanisms of planet formation are more turbulent, chaotic, and productive for wanderers than we had believed. Furthermore, this discovery provides insight into a galaxy filled with interconnections, where fragments of one system can move to another, carrying with them the chemical composition and structure of foreign worlds. As the James Webb Space Telescope continues to observe the universe, its discovery regarding the three interstellar objects will remain a benchmark for what careful and precise observation can yield. It demonstrates that even when astronomers believe they understand the scale of a phenomenon, the cosmos is always capable of surprising us. The discovery that the three interstellar objects are significantly larger than previously assumed is not merely a correction of measurements. It is a window into a greater truth about the multitude and diversity of interstellar travelers. Each of them may be an envoy, but some, like the three interstellar objects, arrive as monumental messengers, altering humanity's perceptions of the galaxy in which it exists. This discovery of the three interstellar objects has opened new horizons for astrophysics. While the confirmation by the James Webb Space Telescope provided an immediate boost to various aspects of science, each requiring careful examination, the most intriguing aspect is that such a discovery compels every discipline, from planetary science to stellar evolution and even galactic dynamics, to reevaluate established concepts. The notion that interstellar space is populated not only by small, icy travelers, but also by massive bodies with complex structures, adds relevance to our understanding of the architecture of the universe. One of the most intriguing areas of research remains the origin of such a massive body. To be ejected from its native system, 3AI Atlas must have experienced catastrophic collisions during its formation. Young star systems represent vast spaces where changes occur under the influence of gravity. Here, gigantic planets can migrate, while smaller bodies are captured and expelled, never becoming full-fledged planets. This indicates that the system to which they belong has undergone particularly tumultuous events. Perhaps several large planets formed in the early stages and actively interacted with one another, or a collision with a nearby star disrupted the system during its formation. In any case, the dynamics required to eject such large objects imply that the expulsion of massive bodies could populate interstellar space with large wanderers like 3I Atlas. This would create an invisible population of monumental travelers endlessly drifting in the void. The detection of their mass also raises important questions about survivability. Interstellar space is nearly empty. It contains only dust, sparse atoms, and streams of radiation. Yet large objects retain much of their structure even after thousands of years of exposure. This means that 3AI Atlas may still hold original records of its native system, encased in layers of rock or ice. For astronomers, this becomes a true time capsule, a preserved relic capable of providing insight into the conditions of a system located light years away. This underscores the importance of studying such objects with a probe in the future, as they provide something akin to direct samples from extraterrestrial planetary nurseries. The scale of 3AI Atlas also affects the physics of gravitational interactions. A massive object moving on a hyperbolic trajectory through our solar system is not a random visitor. It is an active gravitational participant. Even if it never collides with other small bodies, its presence can disturb comets, nudge asteroids, and potentially alter the delicate balance of orbits in regions such as the asteroid belt. These interactions may be subtle, but they highlight that interstellar objects of significant size are not passive. Each one is a driving force of gravitational changes, albeit temporary, in the systems they traverse. However, its scale suggests that deeper layers lie beneath the surface. Larger bodies may differentiate internally due to the heat of radioactive elements or gravitational compression, creating layers of rock, ice, and possibly even reservoirs. This also emphasizes the limitations of previous detection methods. When astronomers first identified interstellar visitors, such as Oumuamua and Borisov, they operated at the limits of observational capabilities, trying to catch faint points moving rapidly across the night sky. However, the fact that 3I Atlas turned out to be significantly larger, yet still underestimated, demonstrates how easily even substantial cosmic wanderers can evade complete characterization without the use of advanced tools, such as Webb observatories. This suggests that many other objects of similar or even greater size may remain unnoticed. They could have passed by us, slipping through the solar system at a time when humanity lacked the tools to detect them. The realization that we are only beginning to grasp the mysteries of interstellar visitors in our galaxy is awe-inspiring. The discovery of the object known as 3I Atlas will likely open up significantly broader areas for research. The galactic context of this discovery is difficult to overstate. The Milky Way represents eternal motion, where stars rotate around their center, interacting with one another, while countless ejected fragments circulate through its vast disk. The existence of such a large interstellar body as 3I Atlas indicates that the galactic ecosystem is much richer than just a collection of star systems. It is a complex network of exchange, where systems shed parts of themselves that become part of the wandering population of the galaxy. Over billions of years, these celestial bodies weave invisible threads of connection, linking distant stars not only through light, but also through matter. For humanity, which has always sought to find its place in the cosmos, such an image is deeply unifying. It implies that our solar system is not isolated, but participates in an ongoing galactic dialogue, captured in the Stone of Ildu. Another dimension revealed by the discovery is the potential role of large interstellar objects in seeding new systems with material. If an object like 3I Atlas were to come under the gravitational influence of a young star system, it could deliver organic or complex compounds across vast distances. This delivery mechanism adds a new layer to theories of chemical evolution, complementing models of the distribution of life's precursors within a single system. Thus, the galaxy may engage in a continuous process of material exchange, where large bodies act as couriers, transporting complex chemistry from one star to another. The confirmation of the size of 3I Atlas enhances the likelihood of this idea, as larger objects are more likely to remain intact long enough to fulfill such a role. It also calls into question the actual frequency of stellar objects of this scale. Astronomers once believed that large ejected bodies would be extremely rare, as it is easier to eject smaller fragments. However, the discovery of the object designated as 3I Atlas calls this assumption into question, leaving open the possibility that we have underestimated the galactic population. If large interstellar planets are common, then our models of star and planet formation must account for the immense forces and inefficiencies associated with such frequent ejections. Entire sections of protoplanetary disks may be scattered across space, representing not only fragments, but also whole embryos of worlds. The galaxy becomes not just a place of formation, but also of constant scattering, where each system serves as both a cradle and a source of wanderers. From a technological standpoint, the discovery of the true size of the object with the designation 3I Atlas highlights the importance of instruments operating in the infrared range. Optical telescopes face limitations due to poor visibility of such distant objects, especially when their surfaces are shaded by organic compounds. In contrast, infrared detection allows for the identification of the faint heat of these bodies, even in insufficient sunlight. The ability of the James Webb Space Telescope to register these weak emissions has enabled astronomers to determine the true size of the object with unprecedented accuracy. This discovery underscores the necessity of optimizing future space and ground telescopes for the search for interstellar wanderers. Missions such as the Caribbean Faith Observatory will soon enhance our capabilities in detecting transient objects. However, the James Webb has demonstrated how important it is to complement the discovery with a more detailed description. The psychological impact of this confirmation should not be underestimated. Humanity has always had an interest in the unknown, and interstellar visitors embody this mystery in the most literal sense. The thought that something vast and ancient, originating from a distant system, is passing by us evokes a deep sense of humility. The realization that this object is much larger than we had assumed amplifies the feeling of awe. Let us recognize that we share the galaxy with these wandering bodies. Their journeys challenge human perceptions of time. Each of them carries an untold story, and the James Webb Space Telescope has provided us the opportunity to read a few more pages of this story, like never before. For theorists studying the evolution of galaxies, this discovery presents a new challenge. Large interstellar bodies may not only wander infinitely, but also exert subtle influences on the structure of our galaxy. Over millennia, their cumulative gravitational effects, however insignificant they may seem, could contribute to the redistribution of matter in the galactic disk. Moreover, collisions between the interstellar bodies themselves, even if they occur quite rarely, could generate streams of debris, forming secondary populations of wanderers. The discovery made by the James Webb Space Telescope regarding the mass of 3I Atlas is directly related to these considerations. It confirms that these bodies may be significantly more massive and therefore more meaningful from a dynamic perspective than previously thought. It is also worth considering the potential role of such bodies in the history of our Earth. Although the likelihood of an interstellar collision with our planet remains extremely low, the delivery of interstellar materials in the form of small fragments is quite probable. If 3I Atlas represents a part of a larger population, then on geological timescales, Earth and other planets could very well have been seeded with particles or even subjected to minor collisions with interstellar wanderers. Such an influx could mix the chemical compositions of various stellar systems, intertwining their evolutionary paths. The discovery of the existence of such large objects makes this possibility even more plausible. It suggests that the galaxy has been engaged in subtle interactions for billions of years. While interest in observations using the James Webb Space Telescope continues to grow, scientists are already beginning to contemplate how to utilize this data. Ideas for missions aimed at intercepting future interstellar objects have become more relevant than ever. A probe designed to meet with a body like 3I Atlas could revolutionize planetology, providing an opportunity for direct analysis of materials from beyond our solar system. The larger the object, the more significant such a mission becomes, as it opens access not only to surface samples, but also to internal structures, volatile substances, and complex organics. Now that 3I Atlas is recognized as significantly larger, the concept of interstellar missions has ceased to be merely speculative. This discovery also prompts reflection on humanity's growing capabilities in perceiving the universe. For centuries, interstellar objects remained unnoticed, their grandeur hidden from view. Only in recent decades have we begun to detect them, and they are already rewriting the history of space. The discovery made by the James Webb Space Telescope demonstrates how each technological achievement expands our understanding, revealing not only new horizons of the universe, but also its complexity. It serves as a reminder that discoveries are not static achievements, but a dynamic process, where each new observation deepens both knowledge and mysteries. The confirmation that 3I Atlas is significantly larger than initially assumed by astronomers opens the door to numerous new interpretations that extend far beyond traditional planetology. The James Webb Space Telescope has not only added a new dimension, but also offered an entirely new perspective for studying space. Its discoveries open up new possibilities for research in fields such as astrophysics, planetary chemistry, astrobiology, and even galactic archaeology, which could not have been realized with smaller objects. Considering the implications for various scientific fields, the scale of 3I Atlas becomes not just a fact about a specific object, but a lens through which one can observe the mechanisms of the universe itself. The possibilities for information preservation also extend to isotopic ratios, which are important markers for determining the origins of cosmic material. Each stellar nursery possesses a unique and characteristic signature, dependent on the environment, radiation exposure, and elemental composition. On Earth, scientists have used isotopic ratios to study the history of rocks and meteorites. However, access to ratios preserved in a large interstellar object would be a true revolution. This could provide information not only about a specific stellar system of origin, but also about the broader galactic environment at the moment of its ejection. In a certain sense, the object known as 3I Atlas may serve not merely as a random visitor, but rather as a galactic archive that holds crucial information about conditions in those regions of the galaxy that humanity has never directly observed. Beyond its chemical composition, its size alters the perception of structural complexity. Larger objects are more likely to exhibit geological processes even on minor scales. Tidal forces occurring during ejections, internal heating from radioactive decay, or differentiation into distinct layers. All these scenarios become quite plausible. If 3I Atlas possesses a differentiated structure with a rocky core covered by icy layers, it could be a miniature analog of icy moons such as Europa or Enceladus. This complex structure opens up the enticing possibility that beneath its surface layers, there may have once existed, or may even still exist, reservoirs of liquid. While no one suggests that ecosystems could thrive in such reservoirs, the potential presence of chemically active environments in interstellar bodies changes the understanding of where and how prebiotic chemistry could have originated in the galaxy. Astrobiologists are particularly convinced of such implications. Massive interstellar bodies capable of containing both organic materials and possibly reservoirs of liquid become ideal candidates for the interstellar transfer of prebiotic materials. If such an object is captured by another system or fragmented while passing near a star, it could widely disperse its chemical cargo. This indeed provides a mechanism for the distribution of the building blocks of life over significant distances. From this perspective, objects like 3I Atlas act as agents of galactic chemical continuity, spreading materials that may influence the emergence of life far from their place of origin. The confirmation of its impressive size only strengthens this viewpoint, ensuring that such bodies are not fragile fragments that easily lose their cargo, but rather reliable messengers capable of enduring long galactic journeys. A broader galactic perspective also benefits from analyzing the frequency of active interstellar objects. If 3I Atlas is not an anomaly, then the Milky Way may be filled with such invisible giants, each of which subtly alters the chemical and dynamic composition of the galaxy. From the perspective of galactic population models, this could lead to a revision of the distribution of mass between stars, planets, and interstellar debris. Traditionally, models emphasize that most of the mass of the galaxy is concentrated in stars and interstellar gas, with only a small fraction attributed to solid bodies. However, if there are indeed many large interstellar objects, then a significant portion of galactic matter may belong to this type. This perspective prompts reflection on the idea that the true architecture of the galaxy encompasses not only stellar systems, but also an extensive and persistent diaspora of planetesimals. The cultural and philosophical resonance of the confirmation of Webb also holds significant weight. Throughout human history, the cosmos has been envisioned as vast yet fragmented, where each star is perceived as a distant island of light. However, the discovery of a large interstellar object crossing our solar system points to a much more interconnected galaxy. These bodies serve as messengers, physical links between distant stars, carrying the stories of other worlds within them. Their impressive size transforms them from fleeting specks into monumental symbols of continuity. This is evidence that the galaxy is not a patchwork of isolated systems, but a dynamic environment of exchange. For those who gaze at the stars, The thought that enormous fragments of alien systems may be within reach enhances the sense of belonging to a greater cosmic whole. From a research perspective, the size of the 3I Atlas object opens up virtually limitless possibilities. Larger bodies provide a greater surface area, stronger gravity for holding landing craft, and more opportunities for stable orbits around them. This makes them significantly more attractive targets for space missions compared to smaller, spinning fragments. Missions could conduct detailed studies of its surface, collect rock samples, and possibly even use underground drills to access deeper reservoirs. If humanity ever launches an interstellar mission within the solar system, a large object like 3I Atlas would serve as an ideal testing ground. The confirmation of Webb not only alters scientific theories, but also stimulates technological ambitions, providing a tangible target for future exploration. The presence of such a large interstellar object also prompts humanity to consider space security from a broader perspective. Although the likelihood of a direct collision remains extremely low, the gravitational disturbances caused by large bodies during the passage of comets and asteroids cannot be ignored. Even a slight change in the orbit of an asteroid, caused by the temporary influence of a giant interstellar body, could lead to significant risks for planets over the course of a century. This adds a new dimension to planetary defense, which goes beyond monitoring debris in our solar system and takes into account the unpredictable impact of interstellar objects. In this regard, 3I Atlas becomes not just a scientific mystery, but a reminder that the galaxy is dynamic and filled with objects that we cannot control. For comparative planetology, the discoveries of the Webb Telescope open up vast possibilities. By studying 3I Atlas and comparing it with bodies in our solar system, scientists can test whether the processes that shaped our world are common throughout the galaxy or unique to our local conditions. If the chemical composition, structure, and characteristics of this object are found to be similar to those observed in comets and asteroids, it would confirm the theory of universal processes leading to planet formation. Conversely, noticeable differences could alter our understanding of planetary outcomes that were previously considered true. Each of these scenarios presents an intriguing opportunity. Similarities indicate common processes in the galaxy, while differences may deepen our understanding of cosmic diversity. The size of the object 3I Atlas also contributes to the development of theoretical models of ejection mechanics. Smaller bodies may be ejected due to relatively weak gravitational interactions. However, to eject something large, it is necessary to study its trajectory and characteristics, which will allow scientists to reconstruct the specific conditions of its ejection. This will provide indirect clues about the planetary architecture of the parent system. Thus, interstellar objects represent not just random visitors, but important hints. Each of them is a piece of the puzzle, suggesting invisible worlds beyond the capabilities of modern telescopes. With the confirmation of data from 3I Atlas, we can speak of new horizons in astronomy.